Okay. Hello, everyone. Welcome to the seminar. Today is my pleasure to introduce Pino Rosolini. He's a mathematician, of course, renowned mathematician. He doesn't need presentation, introduction, but yes, he's going to talk today about ultracompletions. This is a recent work that he has been doing, and I'm very eager to see it. So, thank you.
Thank you. Me too, because while getting ready for this, I discovered I could prove something that I thought I couldn't. And so this is joint work in progress with Richard Garner. I'm going to mention several of the contributions Richard had to the ideas I'm going to present. Any mistake I'm going to make today, though, it's on me, because I've not had even time to talk to him about it. He's on the other, well, on a different side of the world. The word ultracompletion was introduced for two reasons. One, because it's a way of adding freely, in a sense that I will explain later, to a category a certain structure. The difficulty is actually explaining what kind of structure that is. And so it's a kind of completion. That's the word usually used for that kind of construction in categories. And it's ultra because it refers to a structure which should be inherent of ultra products. And I'd be happy to go with you through some little part of the history on the work in ultra products before I start. Rather than having the references at the end, I thought I would put them at the beginning, because at the end then there is no time and it's a pity. And in fact, some of these references are really fundamental. Well, the first one is the place where the definition of ultra product, of the construction of ultra products in model theory, that's a branch of mathematical logic, a very important branch of mathematical logic, appeared, and the fundamental result about the construction of ultra products was mentioned. It's not even stated, and then there is a really nice paper. Not nicely typeset, because LaTeX did not, or TeX, if you like, did not exist at that time. It makes it a little difficult to read, because it was produced by standard printing processes of the time by Frame Morrell and Scott, which extended the construction of ultra products introduced by Wash to what they called reduced direct products. Direct products was at the time the standard denomination of a product of structures. A product of groups was called a direct product. A product of vector spaces was called a direct product. A product of models of a theory was called a direct product. And they introduced something to reduce, to cut, in fact, to quotient direct products, and by means of a filter. Filters at that point became a kind of mathematical structure which was interesting to study, and there were a few, very few, in fact, papers devoted to it. A very interesting one is, well, it's not a paper. In fact, I don't think that all the results in the PhD thesis of Andreas Blass appeared in published articles. It was in the thesis on how to perform constructions on ultra filters. I will get to the notion of ultra filters later on. And at that point, I started getting into the realm of category theory to see what an ultra product construction could do. And in fact, it was thanks to work in algebraic geometry, and Schmid produced a notion of ultrafunctor on categories related to algebraic problems in algebraic geometry. In fact, very big constructions in algebraic geometry, where he had the idea of introducing the notion of ultrafunctor. It's almost what the word says. On the categories he was working with in algebraic geometry, essentially categories of rings, he had the construction of ultraproduct, wash construction of ultraproduct, and ultrafunctors between two such categories would simply preserve ultraproducts. It's direct. And he pointed out that there were very interesting functors in algebraic geometry that had the property of preserving ultraproducts. And then finally, the crucial paper by Michael Makkai on stone duality for first-order logic, which is actually the reason why I'm here to tell you this whole story, appeared. It's a very long paper. I'm going to mention some of the things that appear there, and it defines for the first time an actual abstract structure that resembles that of ultraproducts, which are used in model theory. I should say immediately that you will see also through the lecture that the paper is fairly difficult to read, also because it's very clear that the author is trying as hard as possible to convey to the reader the intuition about the construction he is performing. And I have the feeling, now that I've read that paper a few times now, I have the feeling that Michael was not completely convinced he knew the intuition about what he was doing, but the mathematical results which are there speak by themselves. He had a different presentation of the same structure and of the same result in this other paper in the Annals of Pure and Applied Logic. And then after that, two students in Canada, Marek Zawodowski and Francisco Marmolejo, worked on Makkai's notion of ultraproduct of categories with ultraproducts. Then everything stopped, and after a while, interest in duality, in the general idea of stone duality and of filters reappeared in the literature, but it took at least a decade before it started again. And there was a definite push in recent years, a new notion, definitely different notion of category sustaining a structure of ultraproducts proposed by Lurie in notes available online. Then a paper by Richard Garner on properties of ultrafilters, not really relating directly to the work of Makkai and not even to that of Lurie. And then, at the international conferences in category theory in 23 and 24, Ivan de Liberty Forst and then myself had the possibility of speaking about properties of ultraproducts. And finally, there is a very recent contribution by a PhD student, again, you may not believe it, in Canada, on ultracategories, categories which possibly sustain a structure of ultraproducts on a possible characterization. But what pushed Makkai to introduce the notion of ultracategory? It's Michael Makkai has been a strong advocate of the use of category theory in mathematical logic, and I would say all of his papers can be read and books can be read in that vein. He was essentially following Bill Lovier's intuition that categories were providing structures for logical ideas. And well, I gave you time to read the quote from the introduction of the paper, and with this phenomenon in mind, he says, it is natural to ask, it is really natural to ask. It is very strange that nobody asked that question before 1990, to ask if it is possible to endow the collection of models of a theory with a natural abstract structure so that from the resulting entity, the collection of models with further structure, one can fully recover the theory as a syntactical structure. And as I said, the paper contains several results, and in particular, a characterization of the theory that one can obtain, a way to construct the theory one can obtain. And that theory appeared later to be something that model theorists had already felt the need to introduce. And in fact, Bruno Poisat, in a paper in 83, proposed an extension of a theory by ways of imaginaries. And imaginaries are not the imaginary numbers that you can think of immediately. They are imaginary elements that should be there in case you were able to perform within the theory. And now I'm waving my hands because I'm not really able to get into details of this. If in case you were able within the theory to take quotients of the definable subset that you were handling with the various formulas. And the imaginaries were really the equivalence classes that you would like very much to be able to refer to. Sharon Scheller used the theory of elimination of imaginaries in the book on classification theory. And in fact, that characterization, the one I'm mentioning, the thing that what Makkai obtained was exactly the theory that uniformly eliminates imaginaries, was in a paper that I had with two colleagues of mine, Jacopo Menegger, who was here a few months ago, and Fabio Pasquale. In order to speak of ultra products, I will recall very quickly what they are in the standard condition of the construction on sets. First, I need to tell you what an ultrafilter is. I hope I don't need to tell you what an ultrafilter is, but there are two definitions. You can complain that they're not as succinct as possible. The one on the left now is one of the shortest, but there are many ways to introduce a collection of subsets of a given set I to be an ultrafilter. The prefix ultra refers to the fact that one shows that with those conditions, the filter, the ultrafilter, I'm sorry, is maximal among the filters. But I'm not going to tell you what the filter is, because today is really essential. What is useful to derive from the characterization on the right, on the slide, is that if I take the characteristic function of the ultrafilter, then that is precisely a lattice homomorphisms from that power of the Boolean values 2 into 2. And that's one of the ways of thinking of ultrafilters, in fact. Given an ultrafilter on a set I, and given a family S indexed by I, then one defines the ultra product of the family. And it is defined as a suitable quotient of a collection of products. It is, in fact, in categorical terms, the co-limit of the filter diagram you see drawn in green, and the co-limit, maybe I can go here, and the co-limit is just that thing. At the end, it's a co-limit. It's a co-limit of products. It's a co-limit of limits, and it's bound not to behave very nicely with respect to categorical properties. Usually, one works with limits or just co-limits. And this is a mixture of the two. It works very nicely in model theory, so why not? But from a categorical point of view, one one is puzzled by what kind of properties these things are. And Michael Makkai addressed exactly this problem. So again, what can I say about the categorical properties of a construction of taking an ultra product? It's clearly a functor from the category of families indexed by I of sets into the category of sets, and because it's defined by universal construction. But then I refer to the old paper of Frame, Morrell, and Scott to see some of the canonical properties that I may find. And one which is, now, before I go on, maybe I should tell you that there are so many indices, there are very many indices, that most of the time I tend to use a compact notation with just a dot or a star to refer to the fact that in that position there may be an index, which I hope is clear from the context. If it's not clear from the context, I think, yes, I've expanded it in this case, but as you can see, the slide grows and I can't fit it on the page, and I want to have all these properties on. Let's look at the first one. Given a constant family of sets and given a very simple ultrafilter, an ultrafilter generated by an element of the set I, all those subsets of I that have little I as an element, if you compute the construction of the reduced direct product of the ultra product of that family with respect to that filter, you get a oh, I'm sorry. I'm talking about the second. I'm sorry. Let me start again. Take any ultrafilter and take a constant family, any ultrafilter U, and take a constant family, then the diagonal function from the set S into the direct products of the constant family S, so it's the powers of X, give a possibility of defining a function which is actually an injection into the ultra product. And then what I was saying for the second property, what I was saying is consider the only example of ultrafilter that I can provide here without using the axiom of choice, a principal ultrafilter generated, as I was saying, by an element of the set I. If I take the ultra product, the reduced direct product of the family Si with respect to the principal ultrafilter generated by little I, then I get the single factor Si. And while I should point this out, while the first I know, because it's not difficult to prove, that it's an injection, not necessarily a bijection, I know the second is a bijection. And then again, not really in this notation, but frankly, with a nice point towards category theory, although it was in the late 50s, Frame, Morrell, and Scott prove a formula for iteration of ultra products. And it's the third isomorphism you see on the slide. I don't get into, if you like, I can stop, or you can ask a question about the definition of this ultrafilter given a filter U on the set I and a family of ultrafilters Vi on various sets J sub I, all indexed by I. It's a sort of sum, as the notation suggests, but it's not really that. Another direct result of the definition of ultra product is this about an extension of an ultra filter. It's an extension because the filter U is on the set I, and I is a subset of another set J. But one can extend a filter, and an ultra filter in particular, to the larger set by the condition which is written there. So these were properties. As I say, I'd rather write them like this because there are otherwise too many indices. I will return to them through the talk. I don't suggest that you remember them, but there were certain properties that were expressed by isomorphism conditions, some sort of coherence. And I was mentioning at the beginning the crucial result of about ultra products. There is the theorem of Walsh about families of interpretations of ever first order theory. In fact, take a language and a collection of interpretations for the language indexed by I, and then it is possible to determine when a formula is satisfied by a certain string of interpretations for the variables in the ultra product by evaluating a certain set. And the evaluation of the set is the collection of those indices of those interpretations in the collection S sub I, which satisfy the formula phi. It's essentially recalling the definition of the equivalence relation on the ultra products, and it turns the computations that one should do for the model in an algebraic form. One thing that I would like to mention from my point of view, and this is in fact where I started getting interested in Makkai's paper, is that I was sorry that category theory was not really available at the time Walsh has mentioned the result, because I would have liked very much to see a statement like this, but I'm not going to get into it.
Yeah, I have a question about the previous slide.
Yes?
So until now, you talk about the ultra products of sets.
Yes.
But now you have an ultra product of a family of models.
Yes.
So I guess that you have to define what it means that such an ultra product satisfies an equation.
I stop you. Yes, it's a very good question. I thank you for asking the question. I should have to tell you how to perform an interpretation of each of the basic symbols of the language on the ultra product. Mm-hmm. The thing is just that you do, if I may interrupt and continue answering what I thought was your question, you may do it simply as you would do it on products of structures, products of interpretations, for the first part, and then for quotients of the interpretations.
Otherwise, we could take this theorem as the weight.
Yes, yes. If I may comment on that, it would be cheating. Yeah. Yes, but definitely. In fact, the word cheese like this. Yes. The result I'm getting. I want to mention the result by Makkai before getting on. Because of what Walsh's theorem says, it's easy. It's not easy. It's direct. It's a corollary to check that the ultra product functor from I index families of sets into sets preserves an incredible collection of the categorical structure. Finite products, not necessarily arbitrary products, pullbacks, co-products, quotients of equivalence relations. One wonders, after I've given this list, how could it be that in standard textbooks of category theory, they don't introduce the ultra product construction, because it would be a fantastic example of a functor preserving interesting structures that come elementarily explained in the textbook. In particular, I've listed a few properties which I thought at the time were interesting. since the structure of a category, of a small category within the category of sets, can be expressed by an essentially algebraic theory, it means that, again, always for the same theorem, that the ultra-product construction takes categories to categories, and for the same reason, it takes Grothendieck fibrations to Grothendieck fibrations. So it's not that it preserves everything, but it preserves a lot of things. In particular, because of the first four conditions I've listed, it's just to saying that it's a homomorphism of pretoposes from the pretopos set to the power I to the pretopos set, and by composition, just as I show in the diagram, by post-composition with the ultra-product functor, one could get from the homomorphisms of pretoposes from a pretopos T into the pretopos set an ultra-product construction. The thing is that the category I've listed here, this category, is equivalent to the category of first-order models of the theory T for a particular theory T associated to the pretopos, or vice versa. Given a theory T, I can construct a pretopos, which is still called T, with a different font, which gives me exactly that equivalent. That equivalence. Well, I must admit there is no reason to introduce precisely the category, but the definition is so nice, at least I find it very nice, that I thought it was appropriate to list them, and I spend 3 minutes to comment it. The objects, so suppose you have a theory curly T in first-order logic. You want to define a category, so you have to give objects and arrows. Objects first. The objects are formulas in a doubled list of variables, x and x prime, vector x and vector x prime have the same length and refer to the same sorts if you want to be multi-sorted, and they have to satisfy provably in T, in the theory T, that they form a symmetric relation and a transitive relation. Okay? And
are the lengths of x and x prime the same length, or?
Yes. And they have x prime and x double prime, they are all on the same sort. They are just different copies of a list of appropriate variables. And given lists of appropriate variables x and y, now not necessarily with the same length and with the same sort, the arrows are those relations from the x's to the y's, which are stable with respect to the symmetric and transitive relation as the first condition. I remember there was a point. Can I use it?
Yes.
Now this is the issue. This is better. Are those phi which entail the fact that if they speak of x and they speak of y, then x is in relation with x, because there is nothing ensuring reflexivity up there, but I want to be able to speak of x when I have it in phi with respect to the relation rho, and the same thing for y with respect to theta. And as I said, phi must be stable with respect to the relation rho and the relation theta. You see, if I change the two arguments x and y with rho equivalent x prime and theta equivalent y prime, then I still stay within phi. And finally, I can prove that phi is total with respect to rho, So if I can speak of X in rho, there exists a Y, which is in relation with respect to phi with X, and it is single valued. If X is related phi to Y and is also related phi to Y prime, then Y is not equal to Y prime. Y and Y prime are in the relation. Okay, so essentially, the category one introduces is that of equivalence, no, not equivalence, partial equivalence relations with respect to the theory T, and functional relations from one equivalence, from one quotient to the other. You remember at the beginning I was talking about elimination of imaginaries, and imaginaries were the kind of quotient. Well, this is the basic idea. It's not over here. Yes, yes. There is a note at the bottom because I always forget to mention it. It's there are those two little conditions that have to be satisfied. Yes, please.
I was going to ask about the first one, which seems to me I must not, well, on the left. Yeah. The way I must be hallucinating, it looks like it requires a contradictory object. Or two contradictory objects.
Oh, you're right. You're right, because this Y should be X and this X should be Y. Thank you. Thank you. Thank you. Thank you. It says there are two elements somewhere. One satisfies alpha and doesn't satisfy beta, and the other Y satisfies beta and doesn't satisfy alpha. Thank you. And at last, so to say, I'm not going to give you the definition of ultra-category by Makkai. Makkai takes 30 pages in the paper to introduce the definition. I don't want to spend more than an hour now to give you the full definition. You have to trust me there. I'm sorry. You are welcome. I have the paper with me. I can send you the PDF if you like. It's extremely complicated. Let's start. It's a category K with, for any set and any ultra filter on the set, a functor, which I'm going to denote like that. That's exactly Makkai's notation. If you're worried about equivalence classes, which may appear later, don't worry, we'll try to handle those with a different notation, but that is not an equivalence class. It's just a notation for that functor depending on I and U. And there has to be a functor like that, nothing required about it, but that it is a functor. But then for certain things which are called ultra diagrams, and for other things which are called ultramorphisms, I'm going to show you an example very soon, but I'm not going to tell you what they are, between nodes in the ultra diagram and prime, there has to be a natural transformation like that. It's ghastly to say the same already in this form, and it takes pages to get through the definition, and you get many more pages to get to the definition because there are several constants that have to be introduced. The idea, I was lucky to find a few quotes in papers that I mentioned at the beginning about the construction of, about the definition of ultra-category. This is from Marmoleo's thesis. He's speaking about Makkai's ultra-categories, and he says there is very short supply of canonical maps in or out of an ultra product, as opposed to an honest limit or co-limit. Ultramorphisms, which are those delta up there, ultramorphism try to fix this. At saying something like in the category, in the category K, mind you, it's a natural transformation, so delta applied to an appropriate index gives you an arrow in the category K, and that's saying there should be some morphism when when things go right, but the way to say when things go right is really complicated. There is also a comment in Garner's paper, which I'm going to read, which is very nice. An ultra-category, I think I might have used this as just an introduction to ultra-categories, Makkai's ultra-categories. An ultra-category is a category endowed with an abstract ultra-product, with abstract ultra-product functors, the bracket U, which we have at the top, together with interpretation for any definable map between ultra-products. And the quotes are not mine. What definable means is, well, is the long definition of Makkai. Examples. Well, one thing, maybe I should go back. One thing about the definition is that by default of what an ultramorphism is, set is an ultra-category. Because ultramorphisms are those things that set has, whatever that means. And I'm sorry, I really don't want to go into it. As I say, I will have a simple example later. So there is an example of an ultra-category, set. And again, because it's an essentially algebraic notion, any power of set is also a structure of the same kind. So it's an ultra-category. So set to the power C, any category C, is also an ultra-category. And in fact, it's by the same token that one can prove that pretopose homomorphisms into an ultra-category, which is also a pretopose, form ultra-categories. So the category of models of a theory are examples. I was about to say one could have worked it out from the fact that the ultra products of models are defined from those of sets. But in fact, one doesn't really know what the ultramorphisms are in set, but those which are there by fiat. And so it would be very difficult. The only way to prove that the second line provides examples of ultra categories is by the way of what I said. Powers of sets are ultra categories, and therefore also homomorphism of pretoposes to sets are ultra categories. But now, because we know what the structure on the ultra category of models of the theory T is, it's immediate to check that the forgetful functor from such a category into the category of sets is a homomorphism of ultra categories. And then, and I must admit that already here I was faltering, this category of two objects and a single non-trivial arrow is an ultra category, but the only way I know how to prove it is by way of the retraction to the inclusion of two into the category of sets. The retraction sends a non-empty set to 1 and the empty set to 0. And the only thing I can do is that I can check that that is surjective and it preserves ultra products, and therefore it gives a structure of ultra product on of ultra category on 2. The example of 2 is not present in the paper by Makkai.
So if I understood correctly, being an ultra category is I didn't understand it.
Believe me, but try. Yeah, go ahead.
Okay. One necessary condition for being an ultra category is that for every set of indices I, something happens, isn't it?
Yes, definitely.
Okay, for every index for every set of indices I, and for every ultra filter in that set, you must have some functor.
Yeah.
Okay. I see.
Yes. And moreover, when certain things go right, you should be able to find in the ultra category, not in functors, but in the ultra category, certain morphisms, certain arrows. And let me use that question to go through an example. in the category of sets. Because as I said, the way ultramorphisms are defined is by testing in the category of sets if something happens. So what is, I didn't tell you what an ultra diagram is, but now I'm going to try and tell you. An ultra diagram consists of a graph with two kinds of nodes. Are colored green, can you see that that is green? And those which are colored red. It's actually, it looks like orange from here. Oh, how appropriate, it's orange. And those which are green have to be just objects of the category. Those which are red or orange, whatever, have to be obtained as some sort of ultra product of green objects. Okay? Then, how can I find an ultramorphism? Well, I should find in a diagram like that the possibility of drawing a function because those are sets, from one node, from one object, from one set, sorry, to another, simply because of the construction. So independently of what Si, Si prime, Si double prime, whatever are. Well, up there, in this case, I have an ultra product of the family of the nodes at the bottom. Imagine these are all indexed by the set I. And up there, I have the ultra product, the set ultra product with respect to the principal ultra filter on the element little I. Okay? In set, we've seen it before, is where I got confused with the lines. We know that that is isomorphic to the component Si. Okay? So, and that is totally independent of what S is, whether, Si is, if it is empty, non-empty, whatever. So that green arrow up there is there simply because of the ultra product construction in the category of set. It is an isomorphism, so there is also a canonical arrow function up there. In fact, there are many other canonical arrows because there is the identity arrow on the set Si, and there are all the identities arrows on the other sets, whatever they are. In fact, I cannot imagine any other arrow there, independent of what these sets are. Si can be maybe empty, non-empty, so are the others. It doesn't really matter. The orange, red arrow that appears on top, connecting red nodes with red nodes, there can only be arrows that are obtained from the green arrows by an ultra product constructions. I hope you are still with me. So up there, the red arrow can only be the identity arrow, nothing else, in this present example. In this present example, therefore, the composition of these two green arrows in either direction, which is a canonical arrow, say from the set Si back to the set Si, can only be the identity. So when I start playing with these things, I recognize that in an ultra category in general, there have to be isomorphisms connecting the similar construction. This one, for instance. This is writing exactly that construction, that condition, I'm sorry, with respect to an ultra category. And this is what canonically defined arrows between ultra products may mean. And I've copied there, changing the sets S with object C's, the three conditions about isomorphisms. This is an analysis which unfortunately does not appear in any of the papers that I've mentioned. In particular, the first part that there can be only one natural transformation from the identity to the identity. Moving to the second notion of ultracategory, and we have gone through the worst parts by now, believe me. I'm taking a quote from De Liberti's talk at the Category Theory Conference in 23, which is pretty strong. None of these notions appear definitive when read or encountered for the first time for several reasons. I think I managed to convince you that the notion of Makkai's ultracategory fits a description similar to this. The author tries very hard to make it less strong. In both cases, the definition of ultracategory is very heavy and comes together with axioms whose choice seems quite arbitrary. I'm not sure I agree, but this was stated very strongly at the conference. I was there. And it certainly looks like that. In order to see if Ivan was correct or not, I'm going to take you to the definition by Lurie of what an ultracategory is. For that, well, I hope you've looked at the definition of this other construction of a collection of ultrafilters. Now the ultrafilters, oh yes, it's written, good. This time, the family Vi is not distributed on a family J sub I indexed by I, but always on the same set J. It's a disturbing difference, but it's a difference from the previous cases. And here's the definition of Lurie's ultracategory for your happiness. It looks more decent, definitely. So the first line is the same. An ultracategory consists of a family of functors indexed by the ultrafilters on sets varying, and families of natural transformations of this kind. Don't worry, I'm not going to care very much about the natural transformation, but at least here we know what is required and what one should construct. Are these natural transformations and isomorphism have to satisfy certain conditions? Please bear with me with the next slide, which is terrible, I know. It's just saying coherence conditions that the composition of natural transformations, of certain natural transformation, have to satisfy. The first one is really difficult to draw. The second one looks decent because it's a diagram of natural transformation which has to be equal to another diagram of natural transformation. The diagrams of natural transformation are not pleasant in general, so it's as good as it could be. The other one is more complicated. It's also a diagram of natural transformation, but it has to explain that one natural isomorphism is the inverse of another natural isomorphism. It takes a big poster to put it in one page. It's just suggested there. And then there is the final condition there at the bottom. The delta is a family, and now I'm taking delta on a particular, well, on a general ultrafilter and on a particular family of ultrafilters, which are all principal. And the request is that the delta, which in general is not iso, should be iso for these families. Examples. And now I hope we get down to earth. This example is presented also in Lurie's notes. It's a different presentation, but it's the same. Take a compact Hausdorff space, so a set K with a topology tau, which is compact and Hausdorff, and because it's compact Hausdorff, it is possible to define a notion of limit for families of elements of K indexed by a set with respect to ultrafilter on the set, because by compactness and out-of-ness, the intersection of the closure of these sets of the various images of the family AI indexed by the sets in the ultrafilter has to be a singleton, and the limit is the element. Do correct me if I'm saying something inappropriate. And well, there has to be natural transformations of a certain kind, but the category K is discrete in this case because it's a set. And so those natural transformations can only be the identity. And one has to check that those things provide identical functions, and they do. One is the iteration of limits in a compact outer space. The other is the fact that the constant function converges to its point. Given a distributive lattice, if one takes the homomorphisms from the distributive lattice D into 2, which if you remember the first slides, are just the ultrafilters on D need not be a power of 2. Then, simply by composition with the characteristic function of an ultrafilter, one can get a structure of an ultracategory in the sense of Lurie. And again, well, this time the category is an order, so there are arrows, but the arrows simply are derived from the fact that the definition of the ultrafilter, which was used in Lurie's notion of ultracategory, gives rise to a commutative diagram like that. So it is very easy to check that there are instances of ultracategories in the sense of Lurie. One thing that Lurie says in the paper is that he is well aware of the notion of ultracategory by Makkai, but he has no idea of how the two compare. Whether one is an example of the other or vice versa. Examples. The examples essentially are the same now, because the category of sets is an ultracategory. The structure is exactly the structure that we discovered at the beginning with the paper of Frame, Morrell, and Scott. And here I've sketched, but I really don't want to spend time on it, why the third condition turns into an isomorphism, because of the condition that I told you about uniqueness of natural transformations on certain point of an ultra diagram. Actually, we can prove that an ultracategory in the sense of Makkai is an ultracategory in the sense of Lurie. Because in order, not vice versa, not necessarily vice versa yet, but an ultracategory in the sense of Makkai allows one to construct all the structure that Lurie requires and satisfy the various coherence conditions. And now, oh yes, maybe if I want to get into details, I'll require this lemma for Lurie's ultracategory. One thing which really puzzled me looking at the definition of Lurie is why he used a different construction than that of the co-product of ultrafilters. It's not the co-product of ultrafilters. I'll show you, it shows something like a composition, but in fact, the two are interconnected. One can derive the other easily. And finally, the construction I proposed with, well, Richard and I proposed. I'll tell you, I'll rather get into the story and devote the last 10 minutes of this to. I told you why I was interested in the construction of ultracategories, because I was interested in understanding the theorem of washes in the sense of Grothendieck fibrations. but I wanted to understand, I wanted to be able to say when a Grothendieck vibration was an ultracategory, whatever that means. And one way I know how to do it using category theory is recognize that a standard categorical notion has an algebraic presentation via a completion, and then hopefully see that that completion process takes fibrations to fibrations, which is possible. And in that case, use that completion process on fibrations as well. So I'm reading Makkai's paper. I haven't gone into the problems on really understanding what ultra diagrams were, but essentially with the same idea as Richard, I understood that he was talking about standard arrows between ultra product, whatever that means. And so I thought, well, if I have a category C, and I want to be able to say that there are ultra products values in it, I can just throw them in freely. Suppose I have a set I, an ultra filter U, and a family of objects of C indexed by I. I know I should take the ultra product with respect to U of that family, but the category is just a category, it's not an ultra category. I just add that object, and I do so for all the ultra filters. And then the arrows, and here this is actually an equivalence class. Yes, this is an equivalence class. Well, I defined it as in the case of ultra products, with an equivalence relation that refers to something which is when two things are equal up to the appropriate ultra filter, which is the ultra filter on the right. And I mean, I didn't know whether it worked or not. There were instances of similar constructions I discovered much later on the web, essentially, which provide a different construction of what looks like a different construction of an ultra completion, something trying to do the same, but not the same category. I presented this at the category theory conference last year, and at the end, Richard was very well. I was making this remark during the talk. Richard was in the audience, and at the end, it was very nice to remark that a result that I had, which I'm going to get to in a second, was probably not correct, and he was right. Two things. First, just to make sure, I said I added freely ultra products for families. Can I actually define something like the correct structure? And I can. And I use exactly the construction of the of those strange co-products of ultra filters. And as I told you, the construction of the onset is very peculiar. Ultra products in sets are a filtered co-limit of products. So it's very difficult that a home set preserves such a structure, because usually a home set preserves limits or preserves co-limits depending on its variance. But in the case of the ultra category, homing from an object into an ultra product, a free ultra product, is precisely that property. So you see, homing from KWCK distributes over the ultra product to give a set ultra product, which is a nice property which will come in handy. This is the correction Richard provided. Here I was claiming that the ultra product functor was part of a collax idempotent pseudomonad, but collaxicity was wrong. And in fact, it was good that it was just a pseudomonad, because otherwise I wouldn't have been able to go on. And it goes on like this. Examples. Well, it's always the same examples than before, because we got used to them essentially. The ultra product functors are constructed as you would expect, but this time, because I have my hands on the structure, on the construction of the structure, I can state those two things, that the discrete pseudo-algebras for the pseudo-monad are exactly the compact Hausdorff spaces, and the Posetal pseudo-algebras, so those pseudo-algebras which not are just discrete categories, but are Poset categories, are the compact order spaces, and R there is in italics because I hope that you people can help me check that what I just said there is correct, but it doesn't have to be now. And then there is the standard result coming from the work of Makkai, in particular the second. Given a category of models for a theory, a category of homomorphism of pretoposes from a pretopos T to set, as long as T is not too big, has a generating set of objects, then it is possible to recover the category T as a particular construction of categories. And that's precisely a restatement of Makkai's result. Also, as I was saying, I had the construction that allowed me to go back to Grothendieck vibrations and see how to speak of ultra Grothendieck vibrations, whatever they could be. And finally, we can prove that, one, the ultra completion, which is a fairly simple structure because it's a free structure, so it's easy to work there, is an ultra category in the sense of Makkai, and the proof essentially goes via an application of the Yoneda lemma because of the property I mentioned before. So finally, the pseudo algebras for the pseudo monad on ket, which is given by the ultra completion, is contained in the category, the two category actually, of ultra categories by Makkai, which is contained in the two category of ultra categories in the sense of Lurie, which are category pseudo algebras for the ultra monad. So the three notions, as surprising as it may be, are the same. And I think that is the beginning of what could be a nice story coming. I stop there.
Thank you.
Yes.
The corollary, the last line, these triple bars.
The triple bars,
Logical equivalence?
it's one thing which is very useful, I think, in category theory, is that you can relax your notion of isomorphism to just that of equivalence. It means, in this case, and in fact, I mean, if I go carefully through the details, I can probably say something more about this equivalence, but it means just straight away that there are functors from, say, this category to that category, just take one example, and vice versa, from that category to that category. And what one would hope is that one is inverse to the others. Well, it's not necessarily the case, but if you go around one way, you end up finding something which is isomorphic to the one you started, and also the other way.
So close to the beginning, but maybe not
Yes,
exactly.
not exactly. Up to isomorphism, as one would say. Yes.
So in model theory, the reduced products also play a nice role, and also, for example, ultra powers play a very specific and important role. So are the equivalent ultra functors, ultra product or ultra power functors, or reduced power functors, the product functors?
That's a nice question. I'm not sure I want to answer. It was a nightmare to go through this. it's a nice question. I do not know the answer now. I look forward to looking at it because it's definitely one thing that, of course, one can speak of ultra powers having ultra products, not necessarily about reduced direct products in general. And one can use ultra powers to recover, at least formally, the notion of elementary equivalence, which one can show is actually useful to define certain subcategories of these, but reduced, different kinds of reduced direct products, depending on the kind of filter that one uses, give rise to functors. I have to go back because I want to hear functors of this kind, which enjoy, I mean, it's not the right word, but I use it anyway, better properties that of ultrafilters, because you would be able to say that, okay, they do not preserve the full first order structure, but they preserve exactly this kind of structure, and therefore they preserve certain kinds of co-limits. And that is something that should be looked at again and mixed with this. Maybe I'm exaggerating this point, but the two notions of ultra categories introduced in the literature are very powerful. Nobody but the authors have been able to use them proficuously because they are too complicated. So it's a good question. It takes time to look at it.
Is it possible to endow a category K with two different, essentially different structures of all categories?
Yes. Yes, it is, in general. In general. This is a stupid answer, but it's the only one that comes to mind. A discrete pseudo-algebra, being discrete is just a set. The pseudo-algebra structure gives you the information about the topology.
You can give
And you
topologies,
can give
compact
yes.
house of topologies for set. Yes, right.
Yeah, but it's that's not the right answer. I mean, that's a yes, it's a direct answer. But in fact, we've been looking at richer categories with an ultra category structure to see if they had possibly different structures, and we've not been able to find on set. I believe it's impossible. I just believe it. On a category of models, maybe it's possible. Again, it's something that should be investigated because, yes, there are simple examples.
If I can return to the category.
Yes.
Sorry, the corollary on the last slide.
Yeah.
You seem to say that if the Makkai ultra categories are Lurie ultra categorical, but not necessarily vice versa. So the corollary seems to claim more than you're sure of.
In fact, if you've checked through the slide, I've said the three of them. Okay. I said that Makkais were Luries, Luries were pseudo-algebras, pseudo-algebras are Makkais.
Ah,
and so
I see, okay.
In fact, I'm not sure that's the best way to show the two equivalences, but that's the way how we managed to get to it.
Sorry, I have another.
Please.
I mean, the existence of non-principal ultra filters is like equivalent to axiom of choice. So,
Almost.
yeah.
Yes, very close. Yes.
So a lot, some of category theory is trying to be more constructive, but this part of category theory is totally not, or at least makes good use of the axiom of choice, right?
Okay, that's
Well, it's
Yes.
saying if you have an ultra filter, then you can do it.
Yeah, it's relative
If
to
you
the
have
ultra filters you
enough-
actually have.
Well, so it could be vacuous. If you inject that.
no. There are principal ultra
Yeah,
filters.
you
have
could
lots of
do principle. They're not
You might not have much
interesting. I don't think we need a big complicated theory for them.
Well, three. A year ago, there were three. I mean, a year ago, Richard and I were talking about, but could it possibly be that they are different? And we were looking for counterexamples.
Yeah.
And we've been looking for counterexamples. Actually, this is the place, as you can imagine. I mean, this is strengthening the completeness theorems of first order logic.
Yes.
So here, yes, everything is in not even classical logic, is in ZFC. Yes. And in fact, I'm sorry, I didn't spend time to check it, but it's the only place where a restriction on the size of the category is required. I'm sorry, I went very quickly through that. And having a generating set means essentially that if you really forced me, I would reduce that category to be an equivalent presentation, which is essentially. So it's but again, I know that proof works in ZFC. Everything else works in general. I mean, ultrafilters. In fact, I like the idea that ultrafilters are homomorphisms of lattices, because nobody would worry about, well, of course, homomorphism of lattices must be there. Yes, but then, yeah, no, definitely, they are only if I have yet to. No, it's heavily non-constructive. But then the provides a characterization for intuitionistic theories. I mean, if I may go back to, I can take the advantage of this question, going back to the paper by Makkai. It's an incredible achievement. It's really a beautiful paper. It goes beyond the completeness theorem. And frankly, and I know there are no modern theories here, unless I'm mistaken, it's a pity that in modern theory they haven't considered that paper more closely. I mean, it's certainly very relevant for modern theory.
Which paper?
The paper by Makkai, now I have to go back.
Stone duality.
Stone duality for first-order logic in Advances in Mathematics, 1990.
And when you say it goes beyond the completeness theorem, logic, what do you mean?
Good question. So this is an equivalence. So you may wonder why I haven't drawn that with 3 lines, because it's an equivalence, but it's because I wanted to refer to the functor explicitly, and because there is an explicit representation of the functor. So proving that is an equivalence requires doing 3 things once the proof is set up. And the first one is to prove that that functor is faithful. So it separates arrows in the domain, once it's taken in the codomain. Faithfulness, that proof is essentially the same as the completeness theorem. But then there are 2 more things to do in the setup of Makkai, and those 2 things, well, if they are related to the completeness theorem, I've not been able to see. And certainly I doubt it.
Could you briefly say what they are?
Well, yes. Beyond checking faithfulness, you have to prove that it's full, so that once you have two objects in the domain and you consider an arrow between the values of the two objects in the codomain, well, that arrow also comes from an arrow there. That is fullness. And the second is that, well, essentially the property that I told you before, that every object here is isomorphic to an object in the image of the function. Okay, not necessarily isomorphic, not necessarily natural, because you don't have that possibility yet. And those two properties require, well, fullness says given something, there exists. And the second, I said it explicitly, given an object, there is an object such that. Okay, so in both cases, they are a universally quantified formula of an existential formula. In both cases, you go suppose not, and you set up a theory, at least that's the way I see it, you set up a theory which you prove is consistent. From that, you derive an ultrafilter, and then via that ultrafilter, you get to a contradiction to what you just said.
Productive.
Yeah, it's as I say, it's all very, very strongly non-constructive. I mean, it is non-constructive. I'm sorry, I'm thinking back. It's not constructive in the sense that it uses the axiom of choice, but once you've accepted that you have that choice function, everything else is explicit. I mean, I know I'm just trying to climb a glass wall, but it's I don't know. There may be something there that requires looking at a better structure than the one we're used to using sets. I'm sorry. I have nothing specific to write there.
I'm sorry to keep asking, but
No,
the third item sounded like for every object in the pseudo algebra
Yes,
has an isomorphic object in the
in the domain,
in
in the category T. Yes.
You sort of call this isomorphic completeness.
Well, probably yes, but at the moment no,
Okay.
because I didn't use because it has already a name in category theory, which is a very bad name. So it says to be essentially surjective on objects, which is terrible. But that's the way it is.
Surjective on object.
Essentially surjective, because it's not surjective, but it is surjective up to isomorphism, whatever that means.
Was the word dense used?
I don't know. No, dense is something else. I mean, at least in my dictionary, dense is something else. I may be wrong.
Any other questions? Okay, so let's thank our speaker again.